We've been talking a lot about types of energy and how to calculate those types of energy, and work, which is the change in energy from a force, but we haven't actually gotten down to why we really care about energy. So up to this point in the year, we've analyzed the motion of objects using Newton's laws, using kinematics. That's been our primary tool. Energy gives us a new way of analyzing the motion of objects. And as you're going to see moving forward, there will be problems that we could solve either way. Usually, one way is going to be easier than the other, and we'll start talking about that some once we understand how to use energy to analyze the motion of objects. But the important point for now is that energy gives us a new way of analyzing the motion of an object. So here's why energy matters. Energy is useful because the total amount of energy that exists in the universe is constant, okay? Total amount of energy in the universe is constant. This is a huge, huge idea, okay? So if we added up all the energy of all the objects, their kinetic energy, their potential energy, all the different types of energy, for all the objects in the universe today, that number, that total amount of energy would be the same tomorrow and a month from now and a million years from now. The total amount of energy in the universe is constant. You've probably heard this before, except it was worded slightly differently, that energy is neither created nor destroyed, it only changes forms. This idea is one of the most important ideas that we're going to talk about all year. This is a huge, huge, huge idea. And we're going to look at how we can take this idea and apply it to individual objects. Okay, because we're usually not going to be worried about the total energy of the universe. We're usually worried about the energy of a box sliding across the floor. So we're going to look at how we can apply this idea to individual objects. So for an individual object, okay, what this means is there's only, at least for what we're talking about now, there's only two ways that an object can change energy. Okay, the total amount of energy in the universe has to stay constant. There's only two ways for an object to change energy. The first is changing from one form to another. Okay, so within the object, we go from gravitational potential energy to kinetic, something like that. Okay, the second is if energy is transferred from one object to another through work. We know the total energy in the universe has to stay the same. So if an object gains energy from another object, okay, that means that other object has to have lost the same amount of energy. And that's the second way that the energy of an object can change, is the transfer of energy from one object to another through that idea that we talked about earlier, which is work, by exerting a force over a distance. So money ends up being a really great analogy for energy, and we're going to talk about that some as we introduce these ideas. But the main reason is that much like the total energy in the universe, the total amount of money in the United States, or in the world, I should say, remains relatively constant. I realize there's some complicated economic things with the deficit and exchange rates and all that good stuff, but in theory, the total amount of money would stay the same. The only way people gain or lose money is by transferring it from one person to another. And we'll use that as we go through and introduce these ideas. So the first way that the energy of an object can change is by transferring from one form to another. Okay, so we see here this guy that's falling. This is similar actually to the cart going down the ramp. We're starting with some gravitational potential energy, and as the person falls, that gravitational potential energy is being converted into kinetic. And what's important to note is we start with 1,000 joules of gravitational potential energy. At this midpoint here, our total energy is still 1,000 joules. We just have 500 of it has become kinetic. And then we end with 1,000 joules of energy. So the energy of the object, the total energy of the object, is not changing here. All that's happening is gravitational potential energy is being transferred into kinetic. As I was saying on the last slide, one way for the energy of an object to change is to simply have it transfer from one form to another. And the important concept with this type of transfer, this type of change, is that the total energy of the object does not change in this case. It simply goes from one form to another. Going back to our money analogy, I always think of this like depositing money or withdrawing money from the bank. When you do that, the total amount of money that you have doesn't actually change. Okay, if you go to the ATM and withdraw $50, that doesn't change the total amount of money that you have. You now have $50 more in cash, okay, but where did that money come from? It came from your bank account, so you now have $50 less in your bank account. Those are just two different forms of your money, okay? And all that changed was how that was allocated, right? But the total amount of money that you have is the same still. The other way for the energy of an object to change is through work, okay? When we have a force being exerted over a distance, we can change the energy of an object. So we have two examples here. One, we have a person exerting a force to lift up a rock here, doing work on that rock, and what that does is it increases the gravitational potential energy of the rock. We also have another example over here with a person pushing a box. Same idea, they do work on that box, increasing the kinetic energy of that box. So as we just saw in the examples there, the energy of an object can change when we do work on it, when we have an outside force doing work on it. And what happens in this case is the total energy of the object does change now. Okay? When work is done on an object, it changes the total energy of the object, because what ultimately happens is it allows energy to be transferred from one object to another. So if you go and you push a box across the floor, like we saw in the last example, the box gains kinetic energy, but you are losing energy. You're burning calories. There's lots of processes going on in the body that we're not going to get into, but you are losing whatever energy that the object gains. And through work, you're able to transfer that energy. Going back to our money analogy, I always think of this as getting paid or buying something, okay? When you get your weekly paycheck or when you go out and you purchase something, that does change the total amount of money that you have. Unlike withdrawing from an ATM, okay? When you purchase something or get paid, it actually changes the total amount of money that you have between your bank accounts, between the cash in your wallet. The total amount changes. So keeping in mind these two ideas, I have a quick money analogy here, and then we're going to really introduce the big equation that we're going to be using time and time again. It's going to be our new F equals ma. So here's our example. On Monday, I have $100 in my wallet, and I have $300 in the bank, which means that the total amount of money that I have is $400, assuming there's no other forms of money that I have. And then two things happen throughout the week. On Wednesday, I get paid $50, so that's going to add $50 to the total amount of money that I have. And on Thursday, I spend $120, and so that's going to take away from the total amount of money that I have. And so now I can think about the end of the week, Friday, and I'm told that on Friday I have $50 in my wallet. Okay, and I want to know how much money I have in the bank. Well, I can keep in mind that my total amount of money that I started with was $400. I added 50 and lost or spent 120, and so what I'm left with total is going to be $330. And so that means the amount of money I have in the bank must be $280. Because I know that my total must add up to $330. So how does this analogy help us? Okay, we've talked about how money is much like energy. How does this help us use energy? We know that the only way for the energy of an object, the total energy of an object to change, is through work. Okay, so if we can think about all the forms of energy that an object starts with and calculate the total initial energy of an object, okay, and then we can think about all the work done, all the changes to that total energy, we know the final energy of an object. And we can use that information to figure out how much kinetic energy is left. Okay, much like in the previous example, we used the total amount of money that I had to figure out how much money I have in the bank. Equation-wise, this is what it amounts to. Okay, the initial energy of an object plus the work done is going to be equal to the final energy. This equation is huge. You will be using this equation a ton. This is up there with F equals ma as the two most important equations that you will learn this year. Okay, and so what does it mean? So E initial is the total initial energy of an object. Okay, WNC is the work done by non-conservative forces, and we'll talk about what that means in a second. And E final is the final energy of the object. Okay, and when we say initial and final, we're talking about the total energy, all forms combined. So let's think for a second about this idea here of non-conservative forces and what that really means, okay? And so we have this quick example that we're going to work through that's going to help us understand this. So we have a 2-kilogram object thrown up in the air from the ground with an initial speed of 7 meters per second, and it reaches a maximum height of 2.5 meters. And we want to calculate three things. The first thing we want to calculate is the kinetic energy of the object. So that's going to be 1/2 mv squared, okay, and we can go ahead and enter those things. And we end up getting a kinetic energy here of 49 joules. I'll call that Ki. So that's our initial kinetic energy of the object. The next thing we want to calculate is the gravitational potential energy, which is just given by mgh. We know our mass is 2, our height is 2.5, and we find that our gravitational potential energy here is also going to be 49 joules. Lastly, let's think for a second about the work done by that gravitational force as the object rises to its peak. Okay, so work is given by F delta x cosine theta. We know that the force here is the force of gravity, so mg. All right, our displacement is 2.5 as it rises, and that theta, okay, is going to be 180 degrees because its displacement is going up while that force of gravity is going down, so the angle between them is 180 degrees. And we go ahead and calculate the work done in this situation and find that that work done is going to be equal to negative 49 joules. So that's our work done by gravity. So let's think for a second about these two questions down here at the bottom. Is this a case of kinetic energy being transferred to potential energy as this ball rises to the peak? Okay. Or is this a case of work being done, right? We know we start with 49 joules of kinetic energy here, and at the peak we're going to have no kinetic energy because we're not moving. So should we say, well, that kinetic energy became this 49 joules of gravitational potential energy, or should we say that as it rose to the peak, gravity did negative 49 joules of work on it, all right, taking away all of its kinetic energy? Something else to consider is what will happen after it reaches its peak. It has 0 joules here. What's going to happen is it's going to fall back down, and all that energy that it lost, okay, it's going to gain back. And this right here gets at the heart of what a non-conservative force is, okay? When we have something like gravity where an object rises, loses kinetic energy, but then can fall back down and gain that energy back, we consider that to be a conservative force, okay? And so rather than thinking about the work done by that conservative force, which is not incorrect to say that work was done by that conservative force, but we don't really think about it in terms of that. We think about it in terms of potential energy. We do this because the change is not permanent, okay? Gravity did do work on the object, taking away its kinetic energy, but then gravity gives it its energy back. So we say that that energy was simply stored as potential energy. So this is a really important point when you're doing that conservation of energy equation. When calculating the work, the changes in energy from work, we only are going to consider the work done by non-conservative forces. Gravity and spring forces, and these are the two big ones, are conservative forces. They can be undone, okay? The work done by gravity, the work done by spring forces, all right, can be undone. If they take energy away from an object, they will give it back. So instead, we consider the potential energy that is stored by the Earth object system or the object spring system, okay? That energy is simply stored between the two, and it can be used at a later time. So the big idea here is that gravity and spring forces, we don't think about the work done by them, we think about the potential energy stored by them. And it's no coincidence that we happen to have a gravitational potential energy and a spring potential energy. Okay, so we're not going to think about the work done by them because they are conservative forces. One little tidbit here that you don't need to know for this class but might be of interest. The potential energy of an object or of a system is the same as the work done by that force, just negative. So it's the opposite sign of the work done by that force. And we saw that in the last example. Friction, pushes, and pulls, on the other hand, these are considered to be non-conservative forces, okay? Those are your big three non-conservative forces that you should know and recognize, okay? The work done by these forces cannot be undone. If we have an object sliding across a floor, Okay, and there's a frictional force acting on it, reducing its kinetic energy to zero eventually. We can't undo that change. We can't take that work done by friction and put it back into the object. If you throw an object, okay, by exerting a force over it, all right, and you give it kinetic energy, you can't undo that. You can't take that energy back from the object, all right? So those forces, friction, pushes, and pulls, create permanent changes in the energy of an object, okay? And they are considered non-conservative forces. And so we do want to think about the work done by those non-conservative forces.